Okay, we're going to cover Chapter 30, Sections 4 through 6, some of my favorite topics in all of physics. Some really cool applications here. So we're going to look at a lot of concept questions to really get a feel. This is some challenging stuff. You can try and do a number of concept questions to really get a feel for, and a couple exercises to practice with these concepts surrounding Faraday's law. Okay, so concept question 4. Go look at that one. I'm going to draw it up. We have a ring of wire, so that circle is a wire ring, and it's in a B field that's everywhere pointing out of the page. So B is everywhere out. Okay, so it's filling the ring and everywhere. Okay, and the question is, will a current flow clockwise, counterclockwise, or no current at all if A, the B field is increasing, B, the B field is constant, or C, the B field is decreasing. Okay. So what's the main idea to help answer that question? How is the B field related to the current in this wire loop? The big thing to remember is that the current is driven through Faraday's law. Okay. The current is driven by yeah, it's a lot to write. It took me a while. That's Faraday's law, where we're applying it to a physical wire where current can flow and a wire that has resistance R. Okay, but generally the idea is that if you have a changing magnetic flux, remember that whole integral is magnetic flux, and it's changing in time, then it will create a potential difference through an electric field that's generated, which will induce a current. It will force a current. So this is an induced current, whereas this is an applied B field. So the first thing is keep them straight. Even though this current can now create its own B field, and it will, to oppose that by that minus sign, the Lenz's law minus sign. Okay, so let's think about this. If in A we say that the B field is increasing, B applied is increasing. Okay, what is the direction of the current that's going to flow? So the main idea is that current's going to flow in a way to oppose that change. So this will create its own induced B field, and that B field will point in a direction to oppose this change. So B applied is pointing out. Okay, I can just have this arrow to help. So that's our blue there. B is pointing out, okay, and it's getting bigger, which means the change of the B field is also pointing out. Okay. Since the change is pointing out, that means that the induced B field will point in. Okay, so the induced B field will point in. All right, to oppose the outward increasing. Now, it's not as important that it's pointing out, it's that it's outward and increasing. So the change in the B field's out, it's getting bigger out. So that means the induced B field will be in. To create that induced B field, there has to be an induced current that will flow, and here's better to use our right-hand rule with the curvy thing. I want to create a B field that's pointing in, so my thumb points into the page, and my fingers curl in a clockwise motion. So this leads to a clockwise current. Okay, clockwise current. B. The B field applied, this applied B field is not changing. Well, what is the direction of the current? There is none. If B is constant and A is not changing, the loop's not physically changing, so the flux isn't changing. So the time derivative of something that's not changing is 0. So we get I equals 0 in this case. So that's what's important. It's not about having a B field; it's having a changing B field. Okay. C, B applied is decreasing, so it's still pointing out, decreasing. It's still pointing out, but it's getting smaller now. So the B field's pointing out, there's this blue one pointing out, but it's getting smaller, so that means the change in B field is down. Okay? The change in B field is down. Now, just to clarify, I'm only using this thing as a direction pointer, so it's a little bit clearer. Okay, it's not a right-hand rule thing. So the change is down. Since the B field is pointing up, but it's getting smaller, it means it's getting bigger downward. Getting smaller up is the same thing as getting bigger down. So it's getting bigger down, and we want to oppose that. And so we're going to have a B induced that is pointing out. Okay. So B induced will be out to oppose that change. The B field, the applied, is out but getting smaller, so we want to help it. We say don't get smaller, so we're going to add to it outward so that it can not get smaller. Which, in order for that to happen, so outward, our thumb would be out like that, and I curl my fingers, so that's counterclockwise. Okay, now this is really complicated, so that's why we have a lot of concepts that are going to really hash this out. Okay, let's take a look at 5. Practice with 5. So what we have here is we have a loop of wire held with some non-conducting string or something in the air, and below it is another loop of wire, but one that's connected to a circuit with a switch in it and a battery. Okay. So if that switch closes, current would then flow this way. All right. The question is, at certain times around when the switch closes, what is the current flowing in this top loop? Now note that this top loop is just sitting there and it's not connected to this loop. So the only way current could flow is through Faraday's law, through an induced electric field that drives that current. Okay, so first of all, we need to make sure we have clear what is the direction of the B field created by this loop. This is your applied loop. It's going to create a B field that would then induce a B field through Faraday's law in this one. So again, just have to rehash. There are always two B fields. The one that's applied by something, here it's a circuit, okay, and then the other one that's responding, that's the induced one. Okay, so the first question is, what is the current flowing through here before the switch gets closed? So it's just sitting there open. Is there a B field? No, there's not. There's no current flowing, so there's no B field. But what's more important is it's not changing. It's not that there's no B field, it's that that B field is not changing. It's 0 now, and it's 0 now, and it's 0 now. It's not changing, and that's what's important, is the change of the B field. Okay? It is possible to have a 0 B field at a moment and still create a flux, or an induced current, if it's changing. It's going through 0. We'll do a problem later to see that. Okay, so in part A, current is 0, because that's before the switch is closed. Nothing's happening. Okay, so dB dt is 0. All right, now we flip that switch and we say, what is the induced current immediately after that switch is closed? So just as soon as you close that switch, we measure the current. Okay, now it went from 0 to something in a short amount of time. Well, that is a change in B field. So there was nothing before, and now there's current flowing like this, which, if we do our right-hand rule, curling our hands this way, our thumb points upward. So our B field that's created by this, the applied B field, is like that. And it was 0 and then that, which means the change in B field, dB dt, is also up. Okay, it went from 0 to up, which means final minus initial would be up. So the change in the magnetic field through that loop is up, which means this current will flow such to create its own field that will cancel that up. So it wants to create a downward induced field. And in order to do that, that means looking from above, we'd have to have a clockwise current. So our thumb would point downward. Okay, so we'd have a clockwise. So in B, I would be clockwise. All right. Now C is the switch has been closed for a long time. Well, if the switch is closed for a long time, current's flowing, but is it changing? No, it's not changing. And if it's not changing, that means there's no induced flux, no induced current, because there's no induced electric field to drive that current. Okay, so we have I equals 0 if it is switch has just been closed for a long time. But now in D, we say suddenly we open the switch. What is the current right after you open the switch? That means we break the circuit, so current can't flow anymore. Okay. So first, the magnetic field's pointing up, and then it jumps to 0. So the field's up, but dB dt is suddenly down because it was up, and now it's 0, so that's a change of down. Okay, so in this case, dB dt is down, and the induced field says, no, don't go down, and I want to add to it then. I don't want it to go down. I want to have a B field pointing up. Okay, and so that creates an induced field up, which then would give us a reversed roll of a counterclockwise current. Okay, because the induced field would then be up to keep this from getting smaller, keep this from going to 0. Okay, so again, it's not about having a B field. It's about whether or not that B field is changing. It's not about what direction the B field is pointing. It's what direction is the change in the B field. That's what matters for Faraday's law to generate this voltage and generate this current. Okay, let's take a look at number 6. Okay, so number 6, we've got a loop of wire sitting in a horizontal plane. We have a bar magnet with the north end pointing up, okay, south and down, and we're moving this bar magnet towards it, towards that loop. Is there an induced current? If so, what direction would it go? Okay, well, first of all, what is the direction of the magnetic field from this bar, this applied magnetic field, through the loop? Well, it comes out of north, so we know that the B field is that way. So that's B applied. Okay. Is it getting bigger or smaller? Since the bar is getting closer, we know that the magnetic fields of a bar magnet are bigger when you're close to it. So since the bar is getting closer, that B field is getting bigger. So dB applied, dt is up. Okay. It's pointing up and getting bigger. So dB dt is up. All right. Well, that means that the induced field, B induced, will be down because it doesn't want it to change. It doesn't want it to get bigger upward. Okay, so it's going to be down. And in order for that to happen, looking from the top, my thumb goes down, I'm going to get a clockwise. So the current is clockwise. Okay. So you see all these examples. We first said, what's the direction of the field, the applied field? How is it changing? Or in other words, what's the direction of the change? Okay. Then we know that the induced B field will be opposite that change, and then we would use right-hand rule to see what current would cause that induced B field. Let's try again, number 7. Number 7, we have another loop sitting in a horizontal plane, and we have a bar magnet situated this way, south and north, and it's moving towards it. Is there current in the loop? If so, what direction? In this case, there's none, okay? Because there's no B field though that's going this way. All the B fields are going parallel to the loop, not through the loop, okay? And any piece that has some component up has an equal piece that's pointing down. Okay? So in this case, the flux isn't changing because there is no flux. The integral part is 0 because all the B field dot DAs go to 0. Okay, so that's because the flux is 0. All right, so current is 0. And number 8 is a similar case. It took me a bit of time to draw this kind of complicated. Okay, so we have this tube or something. We've wrapped this coil of wire around it. Okay, and then we have a bar magnet with the south end nearest this coil, and we are asked 3 different cases. In A, the bar is moving into it. We insert this into it. What happens? Does current flow this way through the meter or this way? Left or right or left? Okay. So what's the first thing to ask? First thing is, what is the direction of the applied field through these coils, through these loops? Okay, they point this way because they point into the south and out of the north. Okay, so this is B applied. All right, so we know the applied field is to the left. Okay, in the case A, where it's moving that way, the velocity is that way, so we're moving the bar into it. Is this B field getting bigger or smaller? It's getting bigger because the bar is getting closer. So these fields that are pointing towards the bar are getting bigger and bigger and bigger. Okay, so that means dB, dt are pointing to the left. Okay. And the coil says, I don't like that. So it creates a current that would create an applied field to oppose that change. So it wants to have a B field that opposes that. So this would be B applied or B induced. Because it doesn't want it to get bigger to the left. Okay. And then in order to get that, we have to use our right-hand rule for a curly loop. We want a B field that way. So the current needs to flow out of the page at the top and into the page at the bottom. So it's flowing out here and in, which means it's going to flow that way. Okay. So for that A, we're going to get current that's going to flow to the right, from left to right. Okay, now part B of this question is, you've inserted this bar, now it's sitting there. What is the direction of the current through the meter? Well, I hope you caught on quickly from this problem and from this problem and from the last part of this problem that it's 0. There's no change. There's a magnetic field, but it's not changing. So this is I is 0. And lastly, you now pull this bar magnet back out. Okay, B field's still pointing to the left. That never changed. But now it's getting smaller. So dB dt is to the right. Okay, so the left field's getting smaller, which means it's getting bigger the other direction. And that means the induced field, we want to flip it. And so we want to cancel that. We say don't get smaller. We want to keep it the same. So we want to add to the existing field, okay, or oppose the change. And so that means we're going to have a current that would be to the left, because that's opposite what we needed before. We could show by the right-hand rule, we now need a B field that's to the left, so it's going to curl in at the top, and so it's going to go this way and down. Okay, one more concept question here. Number 9. Okay, this is emphasizing fields. Okay. Oh, sorry, no, it's not. I'm jumping ahead. No, yes, it is. I'm looking at the wrong problem. Okay, so here we have a B field that's everywhere out of the page. And we can measure somehow these curly electric fields that are going like this. All right, so the B field applied is pointing out, and it's curling, and it causes these induced electric fields that are curling around. So remember, this is the way to apply Faraday's law to something physical, to actually measure a current. It requires an object to measure a current. But a potential doesn't need an object. You can have a potential in space. And what's more important is that potential is created by electric fields, which are in space. So there's no wire here. There's no charges that can be accelerated and cause a current. But these are fields. These are induced fields. So is the B field changing? Yes, it must be changing because we're getting induced fields. The only way you can create those curly fields is by having a changing magnetic field. So we know this is changing. So the question is B getting bigger or smaller? Okay, if I placed a wire here with charges in it, the electric field would drive current in that wire in the clockwise direction, which would create a downward magnetic field. So I curl my fingers clockwise, it would create a downward magnetic field. So I know that B induced is down, or let me say into the page. Okay, it's into the page. All right. And if that's true, that means this must be getting bigger, because this is trying to oppose the change in the applied field. And since this is down, that means the change must be up, and this was already pointing up, which means it must be increasing. Okay, very good. Let's move on to the exercise. This first exercise is actually just another concept question. It's similar. So we have a loop of wire that has current flowing through it, current I flowing through it. Okay, and we have this magnetic field that's everywhere pointing into the page. So this is B, pointing into the page. That's what the X's mean. And the question is it getting bigger or smaller? So think about what we've done in these previous problems. What is the direction of the induced magnetic field? Well, this is an induced current because it's got no connections to batteries or anything. And which means, by the right-hand rule, it's flowing clockwise, which means its induced field is into the page. So B induced is into the page. All right? Which means that must be opposite the direction of the change. So that means dB applied, dt, is out of the page. And if that's true, since the field itself, the applied field, is into the page, okay, it must be getting smaller. Okay? Because into the page and getting smaller means it's getting bigger out of the page. Okay? The change is out. And so that means this is decreasing. Okay, let's try one with some numbers on it. All right. What we have is a square loop of wire, and it's got 150 milliamps of current flowing counterclockwise through it. We're told the resistance of the wires is 0.2 ohms, which are not B, R. It's 0.2 ohms, and we're given the length of this square. It's at 8 centimeters to a side. We have a B field that's everywhere pointing into the page. Okay? All right, so with that, our question is at what rate is the B field changing and what direction? Okay? So first let's get the direction. That's going to be similar to these other ones. Go and try that. Okay, since the current is flowing counterclockwise, that means, counterclockwise is this way, that means it creates an induced B field up. Creates an induced B field up. Okay? And since B induced is up and the B applied is down, B applied must be getting bigger. So B applied is increasing. Let's go backwards to check that, make sure it's clear. B field is into the page. It's getting bigger, so the change is into the page, which means the induced B field will be out of the page. And if so, my thumb will point out, my fingers will curl counterclockwise, showing me the direction of that induced current. Okay, so that is correct. And now we just work with magnitudes, and we think, okay, well, how big? Well, we can jump back to our Faraday's law right here, and we can see that R, or I, induced is going to be 1 over its resistance times time rate of change of the flux. Okay. And here we just have to figure out, well, what's changing in time, what's changing in space. Now, thankfully, the field's constant over the area. It's changing in time, but over this integral, it's constant. So right here, it's some value, right here, it's some value. So over this entire area, it's constant. So I can rewrite that into 1 over R d by dt of just b times the area, because it's constant over the area and it fills the entire area, and it's going straight through. So it becomes the b dot dA becomes just b times a. So now we're done with the space part, the integration over space. Now we have to just figure out the time. What's changing here? Well, the area of the loop's not changing. It's staying the square of length L, but b is changing. So we get a over r dB dt. And our question is, how big is dB dt? Well, at what rate is b changing? Well, that's dB dt. That's the same thing as saying is what rate b changes. But solving for dB dt, which is going to be IR divided by A. Okay. And if you plug in your numbers that are provided, you're going to get 4.7 Teslas per second. Okay. Which is a sizable field, but that's per time. And so you can achieve that by having a smaller change in field, but in a smaller time. Okay, very good. Now I'm going to do this last one in a separate video because it's a little bit longer and I want to give some care to it. So I'm going to do this last one in a separate video.